Hey everybody, Mr. Armkey back with you again for CTI 120. Today we're talking Chapter 5 in the networking section, network cabling. So our objectives are to explain basic transmission concepts, including throughput, bandwidth, multiplexing, and common flaws. We're also going to identify and describe physical characteristics and official standards for coax, twisted pair, and fiber optics, as well as their related connectors. Then we're going to compare some benefits and limitations of various networking tools, and then implementing said tools to troubleshoot some common cable problems. So transmission techniques in use on today's networks are complex and varied, and this is because of the different types of media, types of connectors, different types of intermediary devices, and the profusion of end devices that are currently present. So this section is going to cover measurements that indicate network efficiency, as well as obstacles to good performance. So the term we hear most often when we try and talk about the speed of an internet connection is bandwidth. This is the amount of data that could theoretically be transmitted during a given period. The technical definition of bandwidth is the difference between the highest and lowest frequency that a particular medium is able to carry. So if we subtract one from the other, we get the width of the transmittable frequency band, hence bandwidth. To measure the data that we actually can transmit, not that could be theoretically transmitted, but what we're actually getting going is what we call throughput. And then we can narrow that even further into what we call usable data. So this is exempting transfer errors and overhead, the preamble of a frame, things like that, and get what we call good put. So that's actually what we can use at the other side. These terms are commonly expressed in bits per second, which is called the bit rate. So let's look at some measures here. If we have 1 bit per second, that's traditionally abbreviated as 1 BPS. Easy, right? If we have 1,000 bits per second, we will put what's called kilo at the front and make it into a kilobit per second. 1,000 kilobits, or 1,000,000 bits, is a megabit. 1,000 megabits is a gigabit, and 1,000 gigabits is a terabit. Currently, the international underwater fiber optic cables that we see, I believe, can transfer at somewhere around, I think, 60 terabits per second for some of the thicker ones that they use. There's an 8 cable bundle that runs from Spain to Virginia Beach that is owned by Facebook and Microsoft called the Maria cable, M-A-R-E-A. I want to say it's something like 4,400 miles long, and it can run at like somewhere around 60 terabits per second. It's a pretty massive amount. They had just updated the signaling within the last few months. I would have to double check that article, but it is stupid fast. So when we talk about flaws in transmission, we have to talk about unwanted influences. And traditionally, we term these, when it degrades or distorts the signal, as noise. So think about the term noise as it relates to you. If you hear something that's just loud and distracting, we refer to it as noise. Well, we use the same measurement for noise in networking. We use the decibel. And the decibel, I'm sure, as you're aware, is a logarithmic scale. So something that is 100 decibels versus something that is 10 decibels, there's a significant increase in size. It's not just, oh, it's not 10 times as loud. It's like 100 times as loud or 1,000 times as loud. It's really, really a steep curve, if you will. So a little bit of noise goes a long way. What are some different types of noise? Electromagnetic interference. Of course, networking transmissions go on the electromagnetic spectrum, whether they be copper, radio frequency, or light pulses. Now, light pulses are pretty much immune to EFI because of the the difference in frequencies. The frequency of a light wave is so much faster than a standard electromagnetic wave that it's very difficult to compare the two in terms of interference. Interference is usually something that's in a very similar range. So electrical motors, power lines, televisions, fluorescent lights, especially the ballasts, the induction motors that they use to ignite a fluorescent light, that tends to be very negatively impacting for network cabling. And then radio frequency interference can also be part of that problem. So if you have Wi-Fi in an area, it may be more susceptible to certain types of EMI. Then we also have, on a wired interface, what we call crosstalk. So this is where the signal on one wire infringes on an adjacent signal. So let's say we have a standard pair of cables for, any kind of transmission. We have an RJ45 Cat5 cable. We have 8 leads inside in 4 pairs, and each of those 4 pairs are considered a transmit and receive line for that pair. Now with that, if we have 2 cables that are parallel to one another, 2 different RJ45 cables, we generate what's called alien crosstalk. If we have local crosstalk, which is inside of the same cable, that falls into 2 categories, near end and far end crosstalk. Now this is relative to where the observation of the interference is being taken. So near end crosstalk, or NEXT, occurs near the source, near where you are as you're taking the observation. FEXT, or far end crosstalk, occurs at the far end, which is, let's say we're in a data closet. Near end crosstalk would be at the data closet with us. Far end crosstalk would be at an end device on the other end of the patch. So here we have a little illustration that shows what crosstalk looks like between wires in a cable. We've got a black wire there transmitting a signal, and then we've got the green, yellow, and red wires that are affected by the radiation of the signal being propagated inside of the cable. We also have what's called attenuation. Attenuation is the loss of signal strength as it moves away from a source. Like anything else, there's a finite amount of energy that can be imparted to a signal when it is created. Think about throwing a baseball. If you throw a baseball and no one's going to catch it, what catches up eventually? Well, gravity and air resistance. So the ball slows down, loses its ability to move forward, and is going to fall to the ground. We have to remember our laws of motion. A body in motion will remain in motion until acted upon by an outside force. The outside forces in this case being, as I said, air resistance and gravity. The inertia of your initial throw will fade away and no longer be able to resist those opposing forces. Same thing happens here with an electrical signal. The distortion that can be created by losing that signal strength over time, meaning that it's more susceptible to noise, can then become much more pronounced. If we look at the graphic on the right-hand side, figure 5.2, just after we pass the second peak, you can see that the differential between the original wave and the new wave is pretty pronounced. We see that it becomes much more trapezoidal than square. We see a lot more variation along the edges of the signal. So how do we fix this? Well, we have to include what's called a repeater. A repeater is going to take in and repeat a digital signal by regenerating it in its original form. It does this by taking it in and interpreting it. Now, thankfully, we only have 2 possibilities for a signal, a 0 or a 1. We either have a presence or absence of a particular voltage or signal. So it's a pretty quick process, and it's a mechanical one. It's not a whole lot of interpretation that's needed. So this type of device is traditionally included in almost any intermediary infrastructure device. So a hub, a router, a switch, anything like that will probably include that. Now, when it repeats this information, because it's generating a whole new signal based on the original, and of course, if we follow the limits of the length of the cable, we should be able to preserve the original signal fairly easily. So we're going to repeat the signal in its original form without the previous accumulated noise. We also have what we call latency. Latency is the delay between signal transmission and receipt. More often than not, we refer to latency by the RTT, or round trip time. That's the time it takes for a packet to go from the sender to the receiver and back again. So the more latency you have, the more errors that you may see. Packets may actually transition too long and fall out of what we call the time to live, or the hop limit, moving between devices. Latency causes can be things like the cable is too long without a repeater, or there may be no intervening connectivity device that is able to properly process it, or the device in particular that is carrying that signal is slow or otherwise impeded. If packets experience varying delays, they can arrive out of order, producing what's called packet delay variation, or jitter. So whenever you hear a signal that sounds kind of scrambled, almost kind of underwaterish, with an electronic distortion, that's traditionally what we call jitter. Now, when things are being transmitted, we have to deal with how these transmissions are going to communicate with each other over shared mediums. So the NIC, the network interface card, is going to include the direction in which signals can travel and the number of signals that can travel at a given time. We combine these settings to create different methods of communication. Full duplex, which we see there on the right-hand side under option B, also just called duplex, allows the signal to send and receive simultaneously over one medium, so it can do both. Half duplex, which we see in figure C, is where we can travel in both directions, but we can only do one at a time. Simplex, as we see in figure A, is where signals can only travel in one direction and is often called one-way communication. So the representations I like to give are this. Think of a simplex signal as being a radio station or being a radio in your car, or a boombox, old school, what we would have called a ghetto blaster when I was a kid. I don't particularly care for the racial overtones, but I always thought it was a cool name. A simplex transmission is where the radio station would send the music signal and the radio itself would receive it. So if you're, singing along to Run DMC in your room, it's not necessarily going to be the case that, unless they have a listening device planted, that radio station is not going to be able to hear you singing along. On the other hand, the radio station is not able to receive something that it would be transmitted using the transmitter. The full duplex situation that we see just below it is where we would have more of a telephone conversation, where we can send and receive simultaneously. You can have conversations that quote-unquote step on each other. And then C, the half duplex, is more like, think about playing with walkie-talkies when you were younger, or if you work on a construction site and you have one of those little chirpy push-to-talk items. If the line is clear, you can transmit. Otherwise, you can only receive, but you have to initiate who's doing what at the time. So the line can only be one or the other. Here we can see that the speed and duplex configuration can be changed or left on automatic negotiation. It is recommended that automatic negotiation be the case, just so that way if there is a network failure or adjustment, it can automatically correct itself. Now, in order to send multiple signals over one medium simultaneously, we have to incorporate what's called multiplexing. Multiplexing is breaking a single signal channel into multiple smaller channels logically, meaning that we take the bandwidth and subdivide it based on a particular scalar. Let's say if we have 100 megahertz of frequency and we break it into 10 megahertz channels, that would allow us to transmit without any form of overlap. A multiplexer, or a MUX device, combines these channel signals and is required at the transmitting end in order to send the signal combined. The demux, or demultiplexer, has to be able to separate those combined signals on the opposite side. So here we have a very simple diagram of a multiplexer, to where you see multiple signals coming in, being sent as a single signal, and then being taken apart and decoded at the opposite side. The three types of multiplexing we see on copper lines are time division, statistical time division, and frequency division. So time division and statistical time division divide the channel into multiple time intervals, meaning that on a particular group of nanoseconds or milliseconds, it will transmit a signal for project A, and then it will send it for B, C, and D. So let's say that we have 1 second, 1,000 milliseconds, and we break it up into 10 groups of 100. And then project A is able to transmit from 0 to 99, and then from 100 to 199, so on. Statistical time division does something a little bit different by assigning a slot to a node based on priority and need. So this is going to maximize our bandwidth. Let's say we have a really low-end process that doesn't require as much. We can change how it's prioritized in order to give more traffic bandwidth to a much more critical process. Frequency division is where we assign a different frequency band for each communication subchannel, and it's based on not time, but again, the frequencies like we were talking about just a little bit ago. It's just interleaving these different signals together, either based on simultaneous transmission or time-based queuing transmissions. If we're dealing with fiber, then we have what are called wave division multiplexing, dense wave division, and coarse wavelength division. Standard wavelength division carries multiple light signals simultaneously by dividing a light beam into different wavelengths or colors. Wavelength is traditionally represented by the Greek letter lambda. Those of you who are a fan of the Half-Life series will recognize it. It looks kind of like an upside down Y. So if we look at the graphic on the right, we can see the 5 different transmitter and receiver signals are marked as lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. When it passes into the multiplexer, it generates the combined signal that we see in the middle on the main transmission line, and the demux on the far right side is going to separate those signals back into their original configuration. Now, if we use what's called DWDM, or dense wavelength division multiplexing, that is really extraordinary capacity. That's what we would see on the transatlantic cables. This is used on high bandwidth or long distance WAN links in order to facilitate maximum usage of the bandwidth available. Coarse wavelength division is where channels are spaced more widely apart across the frequency band, and the effective distance is more limited because the signal is not amplified to the same degree. So when we talk about fiber, of course, we have to remember when we're transmitting, if you're dealing with single mode or multi-mode fibers, the length of transmission distance is very different. 550 meters versus something around 40,000 meters. It's just a pretty significant change. So here we can see some different multiplexers available on telecomengineering.com. Just a couple of examples. We see 4-channel, 8-channel, 16, and even 18-channel varieties. Coaxial cable is considered a legacy cable, but it is still used. You'll see it, just because it's easy to connect in certain cases. The infrastructure already exists, so why would we replace it unless it fails? What we see here is a multi-layer construction. We have a PVC sheath on the outside. It's the black, shiny plastic that's on the outside. The braided shielding that we see there is usually probably brass. Can sometimes be copper as well. Usually it's unlikely they're going to use copper for the exterior because it is a very valuable metal. It's better to use it for the conductor than just the braid. And then inside the braided shielding, which gives us some flexibility and strength, we have insulation. This is what's called a dielectric insulator. It's combining PVC and usually something like Teflon, very much a non-stick substance, in order to make sure that the cable is still flexible but is able to compress slightly if necessary without damaging the conducting core in the middle. Now again, think about how thick a traditional coax cable is, and then take a look at the thickness of the core, which means that comparatively the copper in the middle is very, very thin, but still able to be flexible and conduct signals pretty substantially compared for something that was put down for the first time probably in the late 60s, early 70s. Now here we have a different type of copper wire called a twisted pair cable. And this is where we have a much thinner diameter, 0.4 to 0.8 millimeters, and they are color-coded and insulated in pairs with a plastic sheath. Each of these two wires are twisted together to make use of what we call the cancellation effect. The idea is that when we talk about cables running parallel to each other and causing interference, we instead want to twist them together so that each point, depending on the tightness of the twist, they're actually running perpendicular to each other. So if we look at figure 5.8 very closely, let me grab my laser pointer and we will take a peek there. If we look right here, we can see that there is a point at which the cables are running in an X shape. Now imagine that this helical twist remains the same as we go up the cable. So at every point, if we rotate the cable and look at it, the cable overlap should be at a 90-degree angle. That allows us to avoid the cross-contamination of the signals because they're constantly running at 90 degrees to one another, which means it's a minimum contact area. In certain cases, these pairs of wires will also be braided together in what we call a shielded twisted pair configuration, which means that we will then have a foil sheath that goes over each individual pair, and then a foil sheath that goes over the 4 pairs altogether. So twisted pair cabling traditionally uses each of these pairs as a send and receive line. If we're talking about fast Ethernet, there's 1 pair for sending, 1 pair for receiving, so there's 2 up lines, 2 down lines. With gigabit, it uses all 4 pairs. So we haven't had a need to supersede twisted pair cabling beyond RJ45 just yet. Anything beyond that, we go for fiber. The wiring specification we use is TIA EIA 568 A and B. The most common twisted pair types we see are categories 3, 5, 5E, 6, 6A, and 7. Cat 6 has a little plastic divider inside the cable jacket, as you'll recall, to help keep those separated. Cat 5E or higher must be used in modern LANs in order to support the necessary speeds. Now here we have a Cat 5E. This is an unshielded twisted pair cable, as we can see from UTP stamped on the cable itself. 24 AWG, which is American wire gauge, and it is 4 pairs. We can see that inside the clear plastic head. The individual insulation of each, and then the foil, and then the copper shielding like we would see with coax, and then the jacket on the outside, makes shielded twisted pair cable very strong, reasonably thicker, and a lot more expensive to produce. Now it does have to be grounded, so the braided copper shielding tends to be the connector to the head that allows the grounding to be performed. If you look at the connector for a coax line, you'll see that there's a screw cap on the outside, and that tends to connect to a metal stem. There's a dielectric insulator on the stem as well, so there's a core and there's a metal conductor on the outside. Very similar with STP for grounding purposes. So here we can see the comparison. We can see the wires are a little bit darker for the standard PVC versus the plenum grade. Plenum is the space between the ceiling of one room and the floor of the next. And if we run plenum grade cable through, we don't use PVC because PVC, if it burns, again we have to think about fire safety, releases a toxic smoke. So that tends to be something that is not a desirable condition for an office building whenever you're dealing with stuff traveling between floors. We don't want to increase the potential danger. Now, because unshielded twisted pair doesn't have any additional shielding besides the plastic sheath, it's much less expensive to create, but we do have to rely on the cancellation effect almost entirely just to prevent the noise and the interference that could occur. Now, STP and UTP can transmit at the same speed, but the amount of potential interference means that the good put that we receive is going to be much higher with shielded twisted pair. The maximum segment length for both is 100 meters on networks that can support between 1 and 10 gigabits per second. Usually the way we divide that up is 90 meters of that, about 200 and, it's going to be 90 times 3.3, so that's 270 plus another 27, so about 300 feet. 300 feet is going to go inside the wall, and then you're going to have another 30 feet that goes between the wall jack and the device. So a network cable that's longer than 30 feet by itself is probably going to be more counterproductive than helpful. So if you're ever running cable and you need to run something really long, make sure that the total length is not more than 100 meters going from the regenerator at the data closet, if it's a router or switch, going to your device. Proper cable termination is a requirement for two nodes on a network to communicate. If you terminate poorly, this can lead to loss of signal, or it can lead to noise in the signal, which is almost as bad, because losing signal is one thing. You can say, okay, let's just switch the cable. But if you've got a poor signal, it just means that it's constantly going to have errors and run slowly. Now, TIA EIA has two methods of inserting our wires. We can see here on the right-hand side the graphics for A and B wiring. All we're doing is transposing where the orange and green pairs are placed. And if we look at the orange and green pairs in 568 A or B, what those are transposing are the transmit and receive lines that we were talking about before. There's no functional difference unless we don't use the same method on each side. Now, if we use the same ends identically terminated, that's what we call a patch cable or straight through. If we do one end reverse, so A on one side, B on the other, we get a crossover. And if we do a variation to where we do what's called a rollover or console cable, we do a 568A and then an inverted 568A on the other side, or B and inverted B. This is what we would use in order to connect a computer to the console port of a router whenever we're making our configuration changes. Power over Ethernet is a standard called 802.3AF from the IEEE, and this specifies a method for supplying electrical power over twisted pair. Remember, as we said, that the gigabit sequence was the only one that used all of the leads. So if we're using gigabit, obviously the injector is a little bit different, but otherwise we're just borrowing some of the lines. It also allows us to filter things by sending them at different frequencies. The amount of power provided is going to depend on whether or not we're going to use a standard or 802.3 AT standard, 15.4 or 25.5. PoE standard specifies two different types of devices, power sourcing equipment and powered devices. The sourcing equipment, of course, is going to bring the power into the connection line, whereas the powered device is going to consume that power on the opposite side. PoE requires Cat5 or better, and the PSE device must first determine, according to the standard, whether or not a node is PoE capable before attempting to supply it with power. So there's a little bit of a handshake situation that has to go on first so that it doesn't cook things that it's connected to. On networks that require PoE but don't have the capable equipment, we can use adapters. So here we have two networks, one of which has a PoE switch, one of them does not, and one of them is using a PoE camera, and one of them is not. So what you see here is that we have the exact same components, it's just whether or not we have to have two separate items to support data and power. On the bottom half, where we see the non-PoE switch, we have to use data and power together only after it passes the injector. So we have to take those two lines separately, combine them using the injector, and pass them across. Once they're received at the opposite end, we can then use the splitter in order to connect it to a non-PoE device or connect directly to a PoE device. So you can take these and kind of break them into 4 segments. So let me grab my pen. I'll show you what I'm talking about. So I'm going to highlight it in this magenta color. So if we consider this, this, and this to be our different options, whereas we've got our, let me switch over to the highlighter, we've got our data and power lines here and here. We can see that those match up. If we were to combine either the PoE or non-PoE switch, either would work for the PoE or non-PoE device. All we see is whether or not we have to do a injector or splitter depending on the ends. Now, for twisted pair cable, we have to determine whether or not we're dealing with a particular speed, and that is determined at layer 1. So if we're hooking up a Cat5 cable to a device that can run something around 100 gigabits, that's a pretty high end. We're probably not going to have the best success, but if we use Cat6 or Cat7, that's going to end up a lot better. A device's NIC is also a limiting factor because that has a maximum network speed at which it can operate. Now, most LANs today use either what's called fast Ethernet or gigabit. Fast Ethernet tends to go just under 1,000 megabits per second, somewhere around the 700 to 800 range. Devices can auto-negotiate for the fastest standard that they have in common. And you'll find that's common for a lot of stuff in networks, is that, okay, I can use A, B, C, and D. This person can use C, D, E, and F. Well, C and D work. We're going to figure out which one is the fastest of those two, and that's what we're going to use. So here we can see the combinations thereof. 100 base T, 1000 base T, and 10 gig base T. And we can see what type of cable is preferred. Now, fiber optics are structured a little bit differently. Again, the size is a big difference as well as the speed. Fiber optics contain glass or plastic fibers that must be absolutely optically pure and are able to transmit things very, very quickly. So we have a pulsing light sent from a light-emitting diode or laser through the central fibers. And in order to insulate those thin fibers that we do not wish to break or damage, we have to surround it with what's called cladding. Now, the cladding is a layer of glass or plastic that surrounds the fibers. It's a different density, and it's usually also opaque so that it reflects light back to the core. You don't want it to attenuate by losing signal into the surrounding insulation. This cladding also creates enough thickness to allow the fiber to bend without snapping. So if we look at the graphic on the right, we can see that the optical fiber is the very thin one here in the middle. It's indicated as one of the 6 little dots in the middle of the cable. The gel filling compound wraps around it. It has what's called a PBT, which is a wrapping tube. We have a strength member in the middle to help insulate. And then we have our hydrophobic mesh, we have our grounding, and then we have our outer sheath. Now this is a very specific one. This is from a website that sells underground fiber optic cable directly. So this is something that we would see in production. So this is a 6-bundle, 6-core, 36-core fiber. It's very, very expensive per foot, but the transmission capability is absolutely unreal. Plastic buffers on the outside go around the cladding. So this is kind of what we would see in the previous slide as wrapping around each of the cladding pieces. It is opaque in order to absorb any light that escapes. Cladding may be opaque with a liner, kind of a foil reflective layer, or it may be translucent with a high reflectivity index. The Kevlar wrap that goes around the plastic buffer, these are what are called polymeric strands, sometimes things like Aramid. These are going to give a lot of flex and toughness to the fiber. Even then, fiber has a limited what we call bend radius. This is the angle to which a cable can be bent and still transmit correctly. If not only for the potential for damage, it's to be able to not have light pulses that are bouncing backwards towards the originator. So over copper cabling, fiber optic is extremely fast. It has a very high noise resistance because imparting noise into a light beam is very difficult to do unless you're using another light beam. They're very hard to break into, so they've got great security. They're able to carry distances that would put standard cable, copper cable, to shame. They're a lot more expensive, and it's very difficult to splice them unless you have those little auto terminators at the end. So you've got some, positive and negatives there from truecable.com. So with fiber optic, our throughputs can go up to 100 gigabits per second per channel. So when we're talking about the transatlantic cables, that's what's called an 8-core bundle. So that's probably going to have at least 8 cores with 8 channels per. So the way those are structured is going to have a big influence on how much data you can actually move per second. It is the most expensive transmission medium. Segments can vary from 2 to 40,000 meters. So 40 kilometers, for those of you who are unaware, is a pretty significant amount of distance. So if we look at the conversion, 5,280 feet in a mile, and then 3.3 feet in a meter, so 3,300. So let me see. That's 40,000. It's roughly 25,000 miles. Pretty significant. Because, if you think about it, the United States is only about 2,500 miles across. Circumference of the Earth is 24,901. So we're actually only about 100 miles shy of being able to wrap the planet in one fiber optic cable without having to instill, a repeater. So that's fairly nuts. So hopefully we'll never run into that. It's really funny. I never looked that up before. We're talking about 40,000 miles. 40,000 miles converts to 24,855, and then 24,901 is the circumference of the planet. So pretty nutty that I've never seen that little confluence before. Single mode fiber consists of what's called a narrow core system, 8 to 10 microns in diameter. The laser light is going to travel over one path. There's very little reflection, and the light doesn't disperse. It can carry signals for miles and miles and miles before repeating. It's rarely used for shorter connections due to cost, and it is often used for what's called the OC38, which is the backbone of the internet. So here we can see a single mode fiber being transmitted via laser. You can see the core listed there inside the cladding. Now, a multi-mode fiber is much more common. That's what you're going to see in common implementation. We've got them over at NA107. We've got cable bundles floating around with that. It's a core that's much larger in diameter, so it's a little bit less sensitive. The cladding is the same thickness, so the cable is thicker in general. It can use either a laser or an LED because the light pulses can travel at different angles. There is a much more there's a much higher sensitivity to attenuation than single mode. These are the types of cables that you use to connect backbone devices as well as connecting a desktop to the network. So this is an end device as well as intermediary device implementation. You may have a transition between SMF and MMF at what's called a fiber distribution panel, or an FDP. So of course, multimode fiber is used for end devices and basic intermediaries, but once we connect to the backbone, we will need to move to a fiber distribution panel. So here we can see multimode fiber, multiple signal paths, and we don't have to use just the laser. Now the connectors for each of these are defined in different ways. Multimode is defined by the number of fibers involved. Single mode fibers are classified by their size and the shape of the ferrule. The ferrule is just the extended tip of the connector, and this is what actually makes contact with the jack receptacle in order to transmit light from the cable into the device. So the different shapes and polishes that are used by single mode fiber can be either what's called an ultra polished, where you have a rounded edge, or an angle polished. Now I like angle polished a little bit more because it does tend to have a slightly more robust contact surface, so it's much less likely to have diffraction or slippage. But as you will remember from physics, anytime you pass a straightened light beam through an angled substance, it will diffract. It will bounce on an angle. So it takes a while for it to collimate or regain its original straight and narrow path. Single mode fiber connectors are traditionally available within either a 1 1/4 millimeter ferrule or a 2.5. The most common 1 1/4 is the local connector, or the LC, sometimes called the Lucent connector because that's who developed it. The 2.5 millimeters will be things like the standard connector or the straight tip. The most common multimode is what's called the MTRJ. The RJ there, of course, still standing for registered jack, just as it does for an RJ45 or RJ11 cable. Now, existing fiber networks may use ST or SC still because the local connector as well as the MTRJ are the most recent. Now here we have what's called a media converter. This is where we're moving between fiber and copper. This allows different segments of network cable to work together. It will complete the physical connection to convert between light wave and electrical signal. This is also the type of interface that we may see to move between multi-mode and single mode fiber. Some switches actually allow you to change and upgrade their interfaces, and back in the day when they started migrating from copper to fiber, they would include sockets called transceivers. These were modular interfaces you could plug in to go from a standard, what was called a 10 base 10 or 10 base 100 connection up to a gigabit connection, so you could move up to 1,000 megabits per second. This was what's called a GBIC, Gigabit Interface Converter, and we can see here on the right, there's a nice iStock photo. It's got the serial connector at the back, and it's got the two single connectors, the subscriber connector, I'm sorry, at the front. These are fiber optics, but they did definitely have ones that were RJ45 as well. Newer transceivers have made the GBIC obsolete, especially because they're much smaller. So SFP, which is probably one of the more common, XFP as well, SFP+, QSFP, and QSFP+, and CFP, which I've not worked with before, but that's the Centum form factor. Now, to avoid a transceiver mismatch, we have to make sure that these devices are paired, because just like everything else in networking, we take the fastest common protocol that they share. So here we have an SFP that slides in to add fiber connectivity to a switch. We can see the little rubber cap on the end. And there we can see the SFP plus and XFP connectors supported by this particular media converter. That's a rack-mounted one. So here we see what's called a BD transceiver, bidirectional. That's what the BD stands for. Allows up and downline transmission, meaning that the fiber cable carries data in both directions, but because fiber has to operate in simplex, that means either that you have two cables connected together or that they are transmitting on a timer. So installing a transceiver means that we just slide it into the socket in the back of the device. Most SFPs will come with a little tab and latch. There's a little press down that they'll flip to be able to move that in place, and it will lock into place when it comes down. And then if you just pull the latch back out, that will allow you to extract the BD transceiver. So here we see some different standards using fiber optic. gigabit comes into 1000 based LX or SX, comes up to 1000 megabits per second, and can run either single or multi-mode if we're talking about LX, or only multi-mode if we're talking about SX. 550 meters in length for multi-mode, 5,000 for single mode. Now, if we want to go up to the full 40,000 meters, the wraparound of the planet, that's 10 gigabase ER or EW. The LW, as well as the SR and LR, can go about 10,000 megabits per second. The maximum length is going to depend on whether you use the SR, which is 300, and the LR, which is 10,000. And again, that's the difference between multi and single mode fiber. Multi-mode is always going to run shorter. Multi-mode fiber diameter cuts down to about 50 or 62.5 microns. The thicker the cable, the shorter it is going to be. Again, because of the attenuation of the signal as the light bounces inside of the single core or multi-core. If we have a fiber type mismatch, that's actually a misnomer, but it is a term we use. It's more of a core mismatch. This is where we have a 62.5 with a 50 lining up. If we have a 50 going into a 62.5, that's not great, but it's more workable because it's a narrowed focus. We have more room on the other end. If we have a 62.5 going into a 50, that's where we can start to lose signals due to collisions. Wavelength mismatch, POF, which is plastic optical fiber, versus SMF and MMF, which are almost always glass or polycarbonate. Those are going to use very different wavelengths, which means that their optical transmission will change due to their density. You can also have issues due to dirty connectors, which is where the cable connectors at the end of the ferrule, if dirty or otherwise contaminated, will cause blockage or mistranslation of the signal moving from medium to medium. So when we're troubleshooting a network, we need to check the indicator lights first. It's almost universal that if you have a steady light, that means you're connected. If you have a blinking light, that means that connectivity is going on. So you'll usually have a left light and a right light on a connector. If the lights are green, that usually means everything's okay. An amber light usually means that there's a problem. It's probably a minor one. And then a red light, if you see one, is a very bad thing. If we suspect that cabling is the problem, we need to be able to deal with our tools properly, know which ones we use to isolate and analyze our problem. So one of the easiest ones you'll deal with is what's called a toner and probe kit, tone generator and tone locator. The toner is a small electronic device that issues a signal on a wire pair, which uses little alligator clips to clamp onto a wire. So the toner emits the tone, as you might have imagined, and then we take the probe and connect it to the other end to see if we can find where the signal is emanating from. So we have to be able to use trial and error to determine where the pair is going to terminate. Unfortunately, this really doesn't tell us anything about the cable itself. It just tells us about what's called continuity, going from one end to the next. So here we can see a graphic of how the toner and probe works together to figure out where the termination of a wire may be. A multimeter is going to give us a little bit more of a characteristic approach of the electronic circuit that we're looking at. We can look at things like resistance, voltage, or impedance, especially if you're working on things like speakers. So a multimeter can measure voltage to make sure everything is conducting correctly. It can check for the presence of noise. It can check for shorts. Continuity testers, these are essentially doing something that the multimeter does, which is checking to see connectivity, but it's a little bit more intense in that it checks for whether or not the signal is being carried completely or not. So this will be making sure that the pairs are all lined up correctly and able to transmit. Very much like the toner and probe, the base unit generates voltage and the remote unit will detect it. Then it will present a series of pass-fail indicators via lights or an audible tone. Some continuity testers will verify unshielded and shielded pairs are correctly paired, as I said, not shorted, not exposed, and not crossed. Fiber optic continuity testers issue pulses of light, which determine the pulses can reach either end. I will save you some money. You don't have to go get a fiber optic continuity tester. You just need a really high intensity LED mag light. Essentially, you take, I usually use like mechanics gloves. So you'll take a mechanics glove, cup your hand, put the fiber in the bottom of your palm, shine the flashlight in the top, and then have somebody looking at the other end, usually again with their hand cupped. If they can see the light flashes, that means that the cable has continuity. Now, if they do not, if it seems to be kind of flickery, or if it seems really weak, then there may be a problem where maybe you have a break or a bounce back point due to the bend radius. Cable performance tester, also called a certifier, is much more detailed. This is going to perform a lot of the same stuff that a continuity tester does, but this can measure not only the length of a cable, but the distance to a connectivity device, termination point, or cable fault. It measures attenuation, it measures NEXT, so you can check your crosstalk. It doesn't see alien crosstalk quite the same way, but it will tell you based on the attenuation if that's occurring. It can check your termination resistance and impedance, make sure that your heads are good quality, making sure that they can pass or fail based on the different category ratings. The thing I like about it too is if you're testing a lot of cable, rather than you having to write down the results on a notebook or a pad, you can actually automatically store those results to a computer database. What I've seen people do before is that the cable usually has a label on the end. They'll go ahead and identify which one they're doing in which order, and then be able to just kind of pass it back in. And then if they have any weird results, they can go back and check the cable later on. It can also graphically depict your attenuation and crosstalk because we are a visual species. It is stuff that we like to be able to see represented by images. We also have what are called TDRs, time domain reflectometer. This is where we issue a signal and measure how it bounces back. So this can indicate the distance between nodes and whether or not the terminators are correctly in place. ODTR, optical time domain reflectometers, use it for fiber. These are going to measure the length of the cable as well as the attenuation over distance. We can find bad splices, breaks, bends, connectors, and measure attenuation. ODTRs can be kind of expensive, so just be aware that it's not necessarily something everybody has in their kit, but because fiber is an expensive medium to work in, if you're certified, it's just kind of the part of the cost of doing business. The OPM, optical power meter, which we see on the right-hand side in the kind of gray and blue there, the TL510, is also called a light meter. This is going to measure the amount of power transmitted on a fiber optic line, so we can actually see in certain units how we can transmit fiber at a given speed, wavelength, etc. You see the lambda symbol on the TL510. It does have to be calibrated very precisely. There's very accurate optical power standards that have to be present. And of course, because we have different transmissions of light waves through different wavelengths based on temperature, the skill of the technician, the connection type, and whether or not we were correctly calibrating the device first will all affect the final test results. So let's go ahead and take a look at our summary as we're finishing up. I know you guys can read it for yourselves, but I'll just give you a little bit while I, of course, renew your contact information. So if you have any questions, you can email me at jearmke063@cfcc.edu, or you can contact me via my Google Voice number, 239-7814. If you have any other concerns besides that, feel free to stop by my office in NB. Other than that, thank you guys for your time and attention, and I will see you all next class.